Okay, so welcome to part B of lecture 3. We're going to discuss the Doppler effect and the twin paradox. Now that we know how to draw Minkowski diagrams, that will help us understand the twin paradox both analytically and visually. Now, what's the Doppler effect? Well, we all know the Doppler effect in everyday life with not with perhaps with light waves, but with sound waves. We know that a train whistle, when the train is approaching us, appears we hear it at a higher frequency than otherwise, and when it's receding, we hear it at a lower frequency than otherwise. And there's an analog for that effect in relativity. Well, there's no medium in relativity, and light travels at a constant velocity, so the details of the formula will be different, but we'll find a similar effect. Okay, and so here I imagine a signal generator at rest in the frame S prime, and S prime is moving to the right at velocity v as usual, and I'm going to pick up the signal in the frame S. Okay, let's say that the signal generator makes a sinusoidal train of waves, and that n waves are produced at a frequency nu zero over a certain period of time delta t prime. Okay, that means that n is equal to the frequency times the time interval, like that. So there are a certain number of n waves that come out, okay, and that number n could be observed also in the frame S, which is the lamp frame in this particular case. Okay, but that fellow is going to observe a different frequency because the wave train, whose length is n times the wavelength, okay, is now given by the distance that the light travels. Okay, so the light is coming at velocity c. So the front of the train, wave train, makes a distance of c delta t, but the pulse generator over that interval moves a distance v times delta t, and so n lambda is the difference of the two. The wave train is squeezed into a shorter distance in this particular situation because the pulse generator is moving at a non-zero velocity. Okay, so we can take this formula, and I can pull out a factor of delta t, okay, and then then it's going to be delta t times c minus v. I can pull out a factor of c, and then I can pull this lambda over onto the right-hand side and find the ratio of c over lambda. But c over lambda is, of course, just the frequency for any wave, any sinusoidal wave. The speed of the wave is the frequency times the wavelength. Okay. So then I've written n in this form, and then I've written n in the other frame in this form. But over here I also observe that I can relate the time interval of the pulse in S prime, call it delta t prime, and call the time interval of the pulse in S delta t, and they're simply related by time dilation. Okay, so the pulse generator is at rest in S prime, so delta t prime is the proper time over which it operates, and that S sees that time dilated. Okay, so delta t is gamma times delta t prime, or in other words, delta t prime is delta t over gamma. Okay, so I'm just applying time dilation, but I'm being careful to understand that the time which is getting dilated is the proper time, delta t prime. So I write it down here. So now I have two expressions for n. All observers agree as to the number of cycles maxima, for example, in the wave train. Information is invariant to transformations. Of course, it's just a number, something you can write down on a piece of paper and share between frames. And so there, I'm able to write n is equal to nu zero delta t over gamma, and n is equal to nu times 1 minus v over c delta t. I can equate those two expressions, cancel off delta t, and get an expression for nu in terms of nu zero, the frequency of the wave in the rest frame of the generator and factors of velocity. And I do my arithmetic, and I see that my prefactor that gets me from the rest frame of the generator to the frame S is given by this kinematic factor, which is characteristic of the Doppler effect. I see that for V positive, okay, so that this pulse is coming toward me, the train is coming toward me, that nu is then higher than nu zero, the frequency is higher, okay, if it's coming toward me, and if it's receding, then V goes to minus V, and then the frequency is diminished. Okay, now we're going to use the Doppler effect to compare clocks in many situations. This will allow us to compare clocks in inertial frames, which are moving relative to one another. And then when I come to general relativity, I might want to compare clocks which are in different gravitational potentials. And again, I can do that by doing a Doppler shift, and the derivation in general relativity in the gravitational field, we'll do that when we get to it. But as far as special relativity goes, this is the basic Doppler effect. Now, you can do the Doppler effect for situations where there might be an angle between the line of sight between the pulse generator and the observer, and there's lots of variations on it. This is the simplest case. The other cases are done by adding a little geometry into the picture, right? Okay, you might have a transverse Doppler effect where this generator is moving straight vertically, and I observe, however, the wave in the lab frame, and I'll find an effect. Okay, and it's just obtained from similar reasoning as to this, and those examples are covered in the textbook, in the problem sets, and such. So we'll be discussing them in recitation section. Let's see. Let's take this formula and apply it to a particular case, leading up to my discussion of the twins. I'll take that V over C is 0.8, a very hefty velocity, and that's nice because then the Doppler effect, this square root of 1 minus V over C over 1 plus V over C, turns out to just be a third. Just do the arithmetic for me. And so in that case, I see that the frequency that is observed of the wave, in the case that S prime is receding from me, that V is negative, I'm doing that particular case here, okay, receding as stated here, is that nu is equal to nu zero divided by 3. So in that particular case, generator might produce one signal per year, then S would observe one signal every 3 years, just divided by 3. The frequency is reduced by a factor of 3. In the case that it's not receding, but the signal generator is coming toward me, then this Doppler effect gets flipped over. 1/3 becomes a 3, and then if the generator produces one signal per year, okay, then the observer would observe three signals in 1 year, or a signal every 4 months. Okay, and we'll use that fact when we discuss the twin paradox. So let's turn to the twin paradox. Okay, and so in this case we begin with twins. I imagine twins, Mary and Maria. Okay, and they unfortunately have a serious fight, and Maria gets upset, and she jumps a rocket ship and blasts off at a velocity of 80% of the speed of light. Okay, and she leaves Mary alone for 5 years on Mary's clock, and then Maria has second thoughts. She misses her sister, and she comes back at the same velocity that she left with, and this is the world line of her sister Mary. This is the world line of Maria, who runs away and then comes back. And when they intersect, she comes back, and they notice that something's not right. They notice that Mary is 10 years older, but Maria has only had 6 birthdays, and she's only 6 years older. So Maria comes back, and she's Mary's junior by 4 years, and they're no longer twins. Well, it sounds a little bit puzzling, okay, and we want to try to understand it. Why is it puzzling? Well, one might talk about it a little bit sloppily and say that, you know, Maria runs away and then comes back, but and from Mary's perspective, of course, Maria is always traveling at a velocity, a speed of 0.8, and so Mary can say that Maria's clocks always run slow, and she can understand that Maria comes back younger than she was when she left. But we can flip the tables, and Maria can say that, well, Mary is running off in the opposite direction, okay, at 0.8 of the speed of light, and so her clock runs slow compared to Maria's clock. So why isn't she younger than Maria when their paths cross again? And that perhaps is the crux of the argument. But certainly it's not very precise, because there is an asymmetry between the two paths. Maria's path, she goes out and then she comes back. Mary is just sitting there. So there's a little bit of there's an asymmetry, but is the asymmetry so essential? Maria says, "Oh, I went out and I came back, but I turned around very abruptly. And on my clock, the amount of time that passes on my clock when I turn around is negligible." Okay? So I'm not making any error when I say that Mary is always aging slower than I am, and I should be the senior when we meet again. Okay? That could be her argument. And we want to analyze those two perspectives and see if we can find the truth, and see that both of them can agree on the description of their paths. Okay. So here I've indicated their paths on a Minkowski diagram. Okay, and here Mary is aging 10 years. Okay, after she's age 5, Maria turns around and comes back to her. Okay, so here's the outbound path of Maria. Okay, and I've indicated that from Mary's perspective, there's a time dilation involved. Okay, gamma is 5/3. So when Maria has aged 3 years, okay, Mary measures those 3 years as dilated to 5 years, and that's indicated in here. Okay, that's indicated here, and that's time dilation, and that continues on, and so Mary says yes. Maria comes back and she's aged 6 years, while I have aged 10 years. And here I've indicated that Maria's trip is outbound at 0.8, and then is inbound at -0.8. And at this point, you know, you could think that Maria accelerates when at this point here when she turns around, but I can change the rules on you a little bit there, and I can say that there's a rocket that goes outbound at a velocity 0.8 times c, and then there's a rocket that comes inbound and crosses Maria's path right here, and the two rockets synchronize their clocks at this particular space-time point, and that second rocket comes in, okay, and meets Mary over here. Okay, perhaps Maria can jump between the rockets from one place, from inbound to outbound. But the point is that I can do the problem without any acceleration. I just have to have two inertial frames. That's the cost I pay, right? This is outbound at a constant velocity. This is inbound at a constant velocity. Synchronize your clocks here, and you still have this space-time diagram. Okay, but we see Mary's perspective clearly. We want to understand Maria's perspective, and so I have to put my t prime and x prime axis on on this figure. Well, that's easy to do. That's nothing new. We've done such things in Minkowski diagrams already. By time dilation, Maria observes Mary's clocks to run slow. Okay, so delta T Maria is gamma delta T Mary. Gamma is 5/3. Okay, and so here it is on a Minkowski diagram, and I've drawn the Minkowski diagram with the proper scales. Okay, so the T prime axis is inclined over here relative to the T axis, and here's my X prime axis. A ray of light would bisect the two. Okay, and I see that lines of constant T prime are parallel to the X prime axis. So when Maria is 3, okay, she says that Mary is 1.8, and that's just over here. Okay, delta T Maria is equal to gamma delta T Mary. Gamma is 5/3. So when Maria is 3, that equals gamma 5/3 times the amount that Mary has aged. Okay, and so you see that the time that Mary has aged is 9/5, which is 1.8, which is on this figure. And so that's just saying that from Maria's perspective, Mary's clocks run slow, and so at the midpoint of her travels, Maria measures the time on Mary's clock and gets 1.8. Yes, 1.8. Okay, and so the time 1 would correspond to 1/3 of that, 2/3 of 1.8, and 3 corresponds to 1.8, like that. So that shows me the outbound travels of Maria from Maria's perspective. Okay, not so hard to understand. Oh, but now we have to face the turnaround. Okay, and at the turnaround, the lines of constant T prime swivel from positive to negative. Remember, if I have I make a Minkowski diagram with a frame S prime which is moving to the left, that then the T prime axis swivels, okay, through an angle of minus theta, and the X prime axis swivels through minus theta, and so the lines of constant T prime are now parallel to the X prime axis and are now slope up, okay, as compared to the first part of the trip, the outbound part of the trip, where the lines of constant T prime, as we saw in the previous picture, okay, point down. So big change from inbound to outbound in the lines of constant T prime. So therefore, I can draw now the whole trip. Okay, so here's the first part of the trip, and I've indicated, that Maria, when she reaches the midpoint, sees that Mary is 1.8 years old on her clocks, on the lines of constant T prime. Okay, now she does the turnaround, and the lines of constant T prime have flipped over to this. See, over to this. Okay, and then I see, I just take this picture, it's symmetric about here, as is symmetric about here. V goes to minus V, okay, theta goes to minus theta, and so where this one had this orientation, this one has that orientation, and so once I have the turnaround, 3 corresponds right after the turnaround to the time 8.2, okay, and then the next year, okay, when I get to year 4 in Maria, okay, it corresponds then to this line, and then at the next year, the year 5 on Maria's clock, it corresponds to this line, okay, and then at 10, Maria comes in and she's 6 years older, while Mary is 10 years older, and okay, and the 8.2 to 10 is chopped up into 3 pieces. Okay. So this is the picture, which is quite remarkable. Okay, because it says that in the turnaround, Maria, of course, doesn't age at all in the turnaround. Okay, but we see that the lines of constant t prime swivel from 1.8 to 8.2, and that during the turnaround, Maria measures that 8.2 minus 1.8, or 6.4 years pass on Mary's clock during her turnaround. That's what the picture says, and that's the asymmetry in the twin paradox. So we see in this particular case, in some sense, right before the turnaround, this is the situation. Okay, Maria says that Mary has aged 1.8, but then at the end of the turnaround, Maria is just 3 plus epsilon years old, and she looks back and sees what age Mary is and gets 8.2. So we have this astonishing, so from Maria's perspective, we have this astonishing aging of Mary of 6.4 years during her turnaround. Okay, so that's the crux of the twin paradox, because we analyze it from the point of view of inbound and outbound trips, okay, and the only asymmetry between Mary and Maria was the fact that Maria had to jump ships at 3 years, and when she jumped ships, okay, her lines of constant t prime swivel, and Mary ages 6.4 years in that period. Now, alternatively, I could attribute that to the acceleration that Maria experiences at the turnaround, and in fact later in the course we're going to do that, and we're going to relate the twin paradox to the equivalence principle in general relativity. That's what's hiding underneath here. We'll have a different perspective into the same principle, and then we'll understand this 6.4 from the perspective of a result of the equivalence principle or acceleration of frames. And that's really why I do the twin paradox this way, because I don't want to just use it as some exercise in special relativity. I want it to be a teaching tool to segue into general relativity, into the effects of acceleration on clocks. Now, there's another way to do the twin paradox. As I indicated before, we did the Doppler effect to set this up. So let's change our tune and just analyze it from another perspective, where Mary and Maria can both keep track of one another's ages continuously throughout both trips. And they do that by sending each other birthday greetings by light rays. Every year, Maria sends Mary a birthday greeting, and similarly, every year, Mary sends Maria a birthday greeting, and we want to see that both pictures are consistent. Okay, so here I have the situation where Mary sends a birthday greeting to Maria on every one of her birthdays. So these are light rays. Okay, they're parallel to the line x is equal to ct. So be careful about that. These are not lines of constant t or constant x. These are light rays. Okay, and so at time, so Mary decides to send a birthday greeting once every year. So it's like a pulse generator, which has a period of 1 year, a frequency of 1 per year. Okay, and so I know how that works. I know that the pulse will be observed by Maria to be Mary and Maria are receding one another. So if a pulse is sent at year 1 on Maria's clock, it's received at year 3 on Maria's clock. Right? That's just the fact here given by the Doppler formula. Okay. The card Mary sends at year 1, Maria receives at her year 3. That's the Doppler effect. Okay. That the frequency nu is equal to this Doppler factor multiplied by 1. That's the frequency by definition of Mary's birthdays, 1 per year. calculating the Doppler effect, it's 1 over 2, it's 1/3, okay? And so, Maria has to wait 3 years to get one signal. Then for the remainder of the trip, Maria receives 9 cards in 3 years, okay? And this is the Doppler effect for the case v goes to minus v, so nu becomes 3, right? And so, okay, and so for the rest of the trip, the inbound, the 1 to 3 covered the outbound portion of the trip, and Maria has to wait 3 years to get 1 card from Mary. On the inbound part of the trip, okay, Mary sends out 9 cards. 3 years pass in Maria's frame of reference, and that's just the fact that when the frames are coming together, Maria measures the frequency enhanced by a factor of 3, not diminished by a factor of 3. So she receives 9 cards in 3 years. The frequency of the reception of the cards is enhanced by a factor of 3, and all is well. She receives all of the birthday greetings from Mary, and Maria understands that Mary, yes indeed, has aged 10 years while she has aged but 6. Okay. Now we can do it the other way around. Okay? To resolve paradoxes, you've got to look at it from both perspectives, otherwise you're fooling yourself. So now we let Maria send the cards. Okay, so now Maria sends cards on her first birthday, second birthday, and third birthday, and they're shown here. These dashed lines are at the speed of light. Okay, they're at the speed of light. They're cutting through at 45 degrees, and so okay, and so Maria is running away from Mary, and so Mary receives, it takes her 3 years to receive one card. That's just a statement that nu is equal to nu 0 over 3. Okay, now Mary is sending the cards, so nu 0 refers to her frequency of sending the birthday greetings, and Maria picks them up at the corresponding frequency, which is enhanced by a factor. Slowed down by a factor of 3, I'm sorry, they're receding. And you see that in the picture. 1 goes to 3. Maria sends a second birthday greeting at her time too. Mary picks it up at when she's 6 years older, and then finally at 3, when Maria has been away for 3 years, she sends a birthday greeting to Mary, and Mary picks it up after 9 years of it. Well, there are then 2 more birthday greetings for Maria to send. She sends one at 4, okay, which then lands like this, okay, coming in at 9 1/3. Then she sends one at 5, which comes in at 9 2/3, and then finally at 6 they coincide. And again, in this particular case, Maria is coming toward Mary, and so Mary receives the postcards at 3 times the frequency that Maria has sent them, and so she receives 1, 2, 3 cards in 1 year, 9 to 10. Okay, and so that's the point. We see that both of the girls agree that Maria has aged 6 years and that Mary has aged 10 years by the exchange of birthday greetings, or in the previous case by looking at the Minkowski diagram and finding that Maria notices that Mary ages 6.4 years during the turnaround. So everyone is in agreement. The truth is that Maria has indeed aged but 6 years, while Mary has aged 10 years, and she'll have to just cope with it. Now in lecture 4, okay, we're going to continue our study of space-time measurements, but we're going to develop the idea of Lorentz transformations and get all of this information in a compact linear transformation to relate measurements in S prime to measurements